Tonight, we're going to look at a telescope image that seems, at first glance, completely ordinary, a faint smudge of light, barely distinguishable from the darkness around it. It looks simple. It looks distant. It looks like something astronomy has been doing for decades. You've heard this before. A new telescope sees farther than the last one. A galaxy is found farther away than expected. The universe turns out to be bigger, older, or more complex than we thought. But here's what most people don't realize. When we say that the James Webb Space Telescope has uncovered one of the oldest galaxies ever seen, we're not just talking about distance. We're not just talking about age. We're talking about the failure of almost every intuitive idea we have about time, light, and what it even means to observe the past. To anchor this, we need a scale that does not fit comfortably in the human mind. Imagine turning on a light and waiting not seconds, not minutes, but years for that light to reach the wall. Now extend that wait until it is longer than the entire span of recorded human history. Then extend it again until it rivals the age of the Earth itself. This is the scale we're operating on before we even begin to talk about galaxies. By the end of this documentary, we will understand what it actually means to see an ancient galaxy, why our intuition about old and far quietly collapses at cosmic scales, and how the James Webb Space Telescope forces us to replace those intuitions with something slower, heavier, and more precise. Our sense of time will no longer be tied to clocks. Our sense of distance will no longer be tied to space. And the word seen will no longer mean what it once did. Now, let's begin. We usually start with something familiar looking up at the night sky. When we do this, it feels immediate. The stars are just there. They appear fixed, calm, and present. Our intuition treats sight as something instantaneous. Light leaves an object, reaches our eyes, and the object exists now, at this moment, exactly as we perceive it. This intuition works perfectly at human scales. When you look at a lamp across a room, the light takes a few billionths of a second to reach you. Your brain is correct to ignore that delay. The world behaves as if vision is instantaneous. But this intuition begins to fracture as soon as distance grows. Light is fast, but it is not infinite. It travels at a fixed speed, about 300,000 kilometers per second. That number sounds enormous, and at human scales it is. Light circles the Earth more than 7 times in a single second. From the moon, light reaches us in just over a second. Even from the sun, the light that warms your skin took about 8 minutes to arrive. Already, we're not seeing the sun as it is now, but as it was 8 minutes ago. This is usually where intuition stops adjusting. 8 minutes still feels like now, but the same rule applies without exception. If light takes 8 minutes from the sun, it takes years from nearby stars. The light from Alpha Centauri, the closest star system beyond the sun, takes over 4 years to reach Earth. When we look at it, we are seeing it as it was 4 years ago, not metaphorically, literally. If something happened there yesterday, we would not know for years. As distance increases, time slips further into the past. A star 1,000 light-years away is seen as it was 1,000 years ago. That light began its journey before telescopes existed, before modern science, before most of recorded history. Yet we still casually say we are looking at a star. Galaxies push this delay beyond anything our intuition evolved to handle. The Milky Way contains hundreds of billions of stars, but it is only one galaxy among hundreds of billions more. Even nearby galaxies are millions of light-years away. The Andromeda Galaxy, our closest large neighbour, is about 2.5 million light-years distant. The light we see from it tonight left when early humans were just beginning to use stone tools. Again, this is not symbolic. It is a direct consequence of light's finite speed. At this point, a subtle shift occurs. Distance and time stop being separate ideas. They collapse into one. In astronomy, to say how far away something is also tells you how far back in time you're seeing it. distance becomes a time machine, not because of exotic physics, but because light takes time to travel. The farther we look, the older the universe we observe. This is the foundation on which the James Webb Space Telescope operates. It is not simply a more powerful camera. It is a device designed to look so far away that the universe itself becomes younger with every increase in distance. But even this description still hides a deeper problem. Our intuition assumes that space is static, that galaxies sit at fixed distances, and that light travels through this space unchanged. That assumption is wrong. The universe is not static, it is expanding. Space itself is stretching. This expansion means that galaxies are not merely far away, they are being carried away from us by the growth of space between us and them. The farther a galaxy is, the faster it appears to recede. This is not because it is moving through space like a rocket. It is because the space itself is growing. As light travels through this expanding space, it is stretched along with it. Its wavelength increases. Blue light becomes redder. Visible light shifts into infrared. This effect is called redshift, and it is one of the most important tools in modern cosmology. Redshift is not just a measure of distance. It is a measure of how much the universe has expanded since the light was emitted. Here, intuition fails again. We are used to colour changes coming from motion, like the Doppler effect of a passing siren. But cosmic redshift is different. It is not about motion through space. It is about the stretching of space itself. The light carries a record of that stretching encoded in its wavelength. The older the light, the more it has been stretched. Extremely distant galaxies have their light shifted so far into the infrared that our eyes cannot see it at all. This is why older telescopes, optimized for visible light, reached a hard limit. They could not see the earliest galaxies, not because those galaxies were too faint, but because their light had been transformed into something invisible to them. The James Webb Space Telescope was built to operate in the infrared. This is not a technical detail. It is a conceptual necessity. To see the early universe, we must see light that no longer looks like light to us. We must detect heat-like wavelengths, stretched by billions of years of cosmic expansion. When Webb detects a faint infrared signal from a distant galaxy, it is not seeing a mature structure like the Milky Way. It is seeing a galaxy in its infancy, when the universe itself was only a small fraction of its current age. In some cases, Webb is detecting light that left its source more than 13 billion years ago. That light began its journey when the universe was less than 5% of its current age. At this point, we need to pause and restate what we now understand. Seeing far away means seeing long ago. Seeing older light means seeing a younger universe. And the farther back we look, the more our everyday ideas about space, time, and light stop working. This is the environment in which claims about one of the oldest galaxies ever seen must be interpreted. It is not a statement about discovery in the everyday sense. It is a statement about pushing observation to the edge of what the universe allows us to see. Beyond a certain point, there is no older light to observe, because the universe itself was opaque. Before a certain age, light could not travel freely at all. The James Webb Space Telescope operates near that boundary. When it uncovers an ancient galaxy, it is not simply adding a data point. It is testing the limits of our models of how quickly galaxies could form, how fast stars could ignite, and how early structure could emerge from the nearly uniform matter of the early universe. We are still operating within observation here, not speculation. Webb collects photons. Those photons have wavelengths, intensities, and spectra. From those, we infer distance, age, and composition. Each inference is layered carefully on top of measurement. Where the measurements end, the inferences stop. And already, at this early stage, something important has happened. Our intuition has been forced to slow down. We no longer think of seeing as now. We no longer think of distance as purely spatial. We are beginning to accept that observation itself is a form of archaeology, where every image is a fossil of light. This shift is necessary, because the galaxies Webb is revealing do not fit comfortably into our previous expectations. They appear massive, structured, and chemically evolved earlier than our models predicted. This does not mean the models are wrong. It means they are being tested at scales they were never before able to reach. For now, we hold on to what is solid. Light takes time. Space expands. Redshift encodes cosmic history. The James Webb Space Telescope is tuned to read that history where previous instruments could not. With this foundation in place, we are ready to go deeper, not by jumping ahead, but by letting the scale continue to stretch until intuition fully gives way to understanding. The moment we accept that looking far away means looking deep into the past, another intuition quietly breaks. We tend to imagine the early universe as empty, simple, and slow. In our minds, complexity takes time. Stars form gradually. Galaxies assemble patiently. Structure feels like something that should emerge late, not early. This intuition comes directly from human experience. Cities take centuries. Ecosystems take millennia. Technological civilizations take thousands of years. Scale up the system, and it feels reasonable to scale up the waiting. But the universe does not share this intuition. When we talk about one of the oldest galaxies ever seen, we're not talking about a faint ancestor of modern galaxies that barely holds together. We're talking about an object that already contains billions of stars, already shows internal structure, and already exhibits chemical signatures of previous stellar generations. This is where discomfort begins, because our intuitive timeline starts to stretch thin. To understand why, we need to slow down and carefully rebuild what early actually means in cosmology. The universe is about 13.8 billion years old. That number is often repeated, but repetition does not produce intuition. If we compress the entire age of the universe into a single calendar year, the Milky Way forms in late August. The Sun and Earth appear in early September. All of recorded human history fits into the last few seconds before midnight on December 31st. By that compression, galaxies discovered by the James Webb Space Telescope are appearing in January, not late winter, early January. But even this analogy collapses under repetition, so we anchor again, differently. Imagine the universe's age as a long road trip. 13.8 billion years is the full journey. For most of that drive, galaxies like our own already exist. What Webb is showing us is not the middle of the trip, but the first few minutes after leaving the driveway, and yet there are already entire cities visible along the road. This is where our expectation fails. We expect the early universe to be smooth, diffuse, and unstructured. In fact, the early universe was smooth, but only barely. Tiny fluctuations in density existed from the beginning. Regions with slightly more matter exerted slightly more gravity. Over time, gravity amplified those differences. Matter flowed inward. Gas collapsed. The first stars ignited. Here is the critical point. Gravity does not wait politely. Once conditions allow collapse, it accelerates. The denser a region becomes, the faster it attracts more matter. This feedback loop means that structure formation is slow at first, then increasingly rapid. What feels too early to us is often exactly when gravity is most effective. The James Webb Space Telescope is sensitive enough to detect the infrared light from these early structures. When it identifies a candidate for one of the oldest galaxies ever seen, the claim rests on redshift. High redshift means the light has been stretched enormously, which means it has travelled through an expanding universe for a very long time. A redshift of 10, 12, or higher corresponds to a universe that is only a few 100 million years old. A few 100 million years sounds like a long time to humans. It is longer than our species has existed. But on cosmic scales, it is a blink. It is less than 3% of the universe's current age. And yet, within that blink, galaxies appear to have grown large enough to challenge our expectations. We need to be precise here. Observation comes first. Webb measures infrared light. From the light spectrum, astronomers determine redshift. From redshift, they infer distance and cosmic age. From brightness and spectral features, they estimate stellar mass and star formation rate. Each step introduces uncertainty, and astronomers are explicit about this. Early galaxy candidates are labelled as candidates because confirmation requires follow-up observations. Still, even with caution, a pattern emerges. These galaxies are not rare outliers. Webb is finding many of them, and they are consistently more massive and more evolved than older models predicted for that era. This does not mean the universe is behaving strangely. It means our mental image of early was built without access to data from that time. Our intuition filled in the gaps with assumptions borrowed from slower, smaller systems. To stabilize our understanding, we need to introduce another scale temperature. The early universe was hot, extremely hot. In its first moments, it was too hot for atoms to exist. As it expanded, it cooled. When it cooled enough, protons and electrons combined to form hydrogen atoms. This event, known as recombination, occurred about 380,000 years after the Big Bang. Before this, the universe was opaque. After this, light could travel freely. That light still surrounds us today as the cosmic microwave background. It marks the earliest time we can observe directly. Everything Webb sees comes after this boundary. So when we talk about galaxies forming a few 100 million years after the Big Bang, we are already well past the universe becoming transparent. Between recombination and the formation of the first stars lies a period called the Cosmic Dark Ages. There were no luminous objects yet. Matter was present, but it had not collapsed enough to ignite nuclear fusion. This period ended when the first stars formed, turning darkness into a patchwork of light. Those first stars were massive, short-lived, and violent. They produced heavy elements and exploded as supernovae, enriching their surroundings. This enrichment is important. It allows later generations of stars to form more efficiently. It also leaves chemical fingerprints that Webb can detect. When Webb sees signs of elements heavier than hydrogen and helium in an early galaxy, it tells us something crucial. It tells us that at least one generation of stars lived and died before the light we are seeing was emitted. In other words, even these ancient galaxies already have a history. This is another intuition breaker. We imagine the first galaxies as pristine beginnings. In reality, by the time galaxies become visible to Webb, they are already products of multiple cycles of formation and destruction. The universe does not start gently. It starts intensely. Let's pause again and restate where we are. We now understand that early does not mean simple. A few 100 million years in the early universe can be enough for complex structures to emerge. Gravity accelerates collapse. High temperatures and densities speed up processes that would be slow today. And Webb is observing this era directly, through light that has been stretched into the infrared by cosmic expansion. Now we confront another hidden assumption that galaxies form in isolation. They do not. Galaxies grow through mergers. Small structures collide and combine to form larger ones. In the dense early universe, mergers were more frequent. Space was smaller. Matter was closer together. Interactions were inevitable. This means that early galaxies could grow rapidly by absorbing their neighbours. What looks like an impossibly massive galaxy for its age may actually be the product of many smaller systems coming together quickly. Again, our intuition resists this because we picture collisions as rare events. In the early universe, they were common. The James Webb Space Telescope does not see these mergers directly in most cases. What it sees are their results: irregular shapes, intense star formation, and unexpected mass. From these observations, models are adjusted, not overturned, but refined. It is important to emphasize restraint here. Scientists are not rewriting cosmology because of a single image. They're comparing Webb's findings against simulations, adjusting parameters, and testing consistency across many observations. This process is slow and careful, mirroring the calm tone we are maintaining here. There is no crisis. There is tension, and tension is productive. As we move deeper, another intuition must be replaced. We tend to think of telescopes as passive observers, simply magnifying what is already there. Webb is not passive. Its design choices actively shape what it can reveal. Its large mirror collects faint light. Its instruments separate wavelengths with extreme precision. Its position far from Earth keeps it cold, minimizing interference. All of this is necessary because the signals from the earliest galaxies are weak. By the time their light reaches us, it has been diluted across expanding space for billions of years. Detecting it requires patience, sensitivity, and an acceptance that we are operating near fundamental limits. And this brings us to an important boundary. There is a limit to how far back we can see, not because of technology alone, but because of physics. Before recombination, the universe was opaque. No telescope, no matter how advanced, can see beyond that wall using light. Webb approaches that wall, but it cannot cross it. This is not a failure. It is a definition of the observable universe. So when Webb uncovers one of the oldest galaxies ever seen, it is operating at the edge of what observation allows. It is not peering into the absolute beginning. It is observing the universe as soon as it became capable of producing light-bearing structures. We end this stretch of understanding with a stable frame. The early universe was dense, hot, and dynamic. Structure formation was rapid, not sluggish. Galaxies could grow surprisingly fast through collapse and mergers. And the James Webb Space Telescope is revealing this reality not by speculation, but by measuring ancient light that has travelled nearly the entire age of the cosmos to reach us. Our intuition is no longer fighting the idea of early complexity. It is beginning to accommodate it, and that accommodation will be tested even further as scale continues to expand. As our intuition adjusts to the idea that complex galaxies can exist very early, another assumption quietly lingers that once light leaves a galaxy, it travels unchanged through an otherwise empty universe until it reaches us. This assumption feels reasonable. In everyday experience, space is just where things are not. It is absence. Nothing happens there. Light crosses it without interference. At cosmic scales, this idea fails completely. Space is not a passive stage. It has properties. It evolves. And most importantly for what the James Webb Space Telescope observes, space expands, not outward into something else, but everywhere, all at once. Every region of space stretches relative to every other. There is no center and no edge. This expansion is not something galaxies do. It is something space itself does. We need to slow this down, because expansion is one of the most misunderstood concepts in cosmology. Our intuition tries to picture galaxies flying away from each other through pre-existing space, like debris from an explosion. That image is wrong. Galaxies are mostly not moving through space at extreme speeds. Instead, the distances between them increase because the space in between grows. An analogy is sometimes used here: dots on the surface of a balloon moving apart as the balloon inflates. But even this analogy must be used once and then discarded. The balloon has an outside and an inside. The universe does not. The balloon stretches into something. Space does not. The only part that matters is the stretching itself. This stretching has a direct, unavoidable effect on light. As light travels, its wavelength is stretched along with space. Short wavelengths become longer. High-energy light becomes lower-energy light. This process is continuous. It does not happen all at once. Every moment the light is in transit, space stretches a little more, and the light stretches with it. This is cosmological redshift. It is not a measurement trick. It is a physical transformation of the light itself. When the James Webb Space Telescope detects infrared light from an ancient galaxy, that light was not necessarily infrared when it was emitted. It may have started as ultraviolet or visible light, produced by hot young stars. Over billions of years of travel through expanding space, it was stretched into the infrared. By the time it reaches Webb, it carries a record of the universe's expansion encoded in its wavelength. This is why redshift is such a powerful tool. The amount of stretching tells us how much the universe has expanded since the light was emitted. More expansion means greater redshift. Greater redshift means earlier emission. Distance, time, and expansion collapse into a single measurable quantity. But here is where intuition breaks again. We're used to thinking of distance as something fixed. A galaxy is 10 billion light-years away as if that were a static number. In an expanding universe, this is not strictly true. The distance between us and the galaxy has changed while the light was travelling. It was closer when the light was emitted. It is farther now. This creates a subtle but important distinction. There are multiple ways to define distance in cosmology: how far the light has travelled, how far away the galaxy was when the light was emitted, and how far away it is now. These are not the same number. None of them are wrong. They answer different questions. Our intuition wants one distance. Reality offers several. The James Webb Space Telescope does not measure distance directly. It measures redshift. From redshift, cosmological models convert that measurement into estimates of age and distance using well-tested equations. These models depend on parameters like the rate of expansion of the universe. Those parameters are constrained by independent observations, including the cosmic microwave background and large-scale galaxy surveys. This layering is important. Observation sits at the bottom, inference sits on top. Modelling connects them. Where uncertainty exists, it is tracked explicitly. When Webb identifies a galaxy with an extremely high redshift, it is telling us that the light has been stretched by a large factor. For example, a redshift of 10 means the universe has expanded by a factor of 11 since the light was emitted. A wavelength that started at 1 unit is now 11 units long. Repeat this number: 11 times stretched, 11 times diluted, 11 times shifted toward invisibility. At a redshift of 12, the factor becomes 13, 13 times stretched, 13 times expanded, 13 times further removed from the conditions under which it was created. Each increase in redshift pushes us deeper into a regime where everyday language begins to fail. Now we need to confront another intuition brightness. We often assume that distant objects are faint simply because they are far away. This is true, but incomplete. In an expanding universe, brightness diminishes for multiple reasons. The light spreads out over a larger area, the energy of each photon decreases as its wavelength stretches, and the arrival rate of photons slows because time itself is dilated by expansion. These effects compound. A galaxy in the early universe is not just far. Its light is weakened in every possible way. By the time it reaches us, it is a fragile signal riding just above the noise of the universe. This is why detecting early galaxies is not just about seeing farther. It is about separating an extraordinarily faint, stretched signal from everything else. Webb sensitivity allows it to do this, but only barely. Many of the oldest galaxy candidates are detected as just a handful of photons accumulated over long exposures. We pause again to restate. Space expands. Light stretches with it. Redshift encodes that stretching. Distance is no longer a single idea. Brightness fades through multiple mechanisms. The earliest galaxies are not just distant, they are transformed by the journey their light has taken. Now consider what this means for interpretation. When Webb observes an ancient galaxy, it is not seeing a frozen snapshot. It is seeing the integrated light from many stars, each with its own history, filtered through billions of years of cosmic expansion. Extracting information from this light requires models of stellar populations, dust, gas, and star formation. Each model is tested against known physics. This is where caution becomes essential. Some early Webb results initially suggested galaxies that were too massive, too bright, too mature. Follow-up analysis refined those estimates. Dusk can redden light. Young stars can dominate brightness. Assumptions matter. This process is not a correction of mistakes so much as a sharpening of tools. Webb did not break cosmology. It forced cosmology to confront data in a regime it had never occupied before. Another intuition quietly dissolves here, that there is a clear boundary between observation and theory. In practice, they are intertwined. Observation provides constraints. Theory provides interpretation. Neither stands alone. When Webb uncovers an ancient galaxy, the discovery is not complete until models can consistently explain it. And sometimes, models must change. This does not mean abandoning established physics. Gravity still behaves as expected. Expansion still follows known laws. Nuclear fusion still powers stars. But the timing, efficiency, and environment of these processes in the early universe may differ from earlier assumptions. The universe was denser, gas cooled differently. Feedback from stars and black holes may have been stronger or weaker. We do not speculate wildly here. We move incrementally. Each new observation tightens the allowable range of models. Each confirmed galaxy at extreme redshift narrows the space of possibilities. There is also a hard observational boundary approaching. As we look to higher and higher redshifts, galaxies become rarer, fainter, and harder to confirm. At some point, there are no galaxies yet. Before the first stars formed, there were no luminous structures to see. Webb cannot show us that era directly. It can only approach it. This approach is not dramatic. It is quiet. It is defined by diminishing returns. Longer exposures yield fewer photons. Candidate galaxies require more confirmation. Uncertainty grows. And this is where the phrase, "one of the oldest galaxies ever seen," must be held carefully. It does not imply finality. It does not imply a record that will stand forever. It marks a moving frontier, advancing slowly as instruments improve and understanding deepens. We end this stretch with a stable understanding. The universe's expansion reshapes light itself. Redshift is not a label, but a physical history. Distance, time, and brightness intertwine. The James Webb Space Telescope operates by reading this history from the faintest possible signals, and as it does, it forces us to abandon static ideas of space and replace them with a dynamic, evolving framework that can support observation at the edge of the observable universe. As we push closer to the earliest observable galaxies, another deeply rooted intuition begins to fail: the idea that seeing an object tells us exactly what it is. In everyday life, this works well. When you see a tree, you know it is a tree. When you see a building, you know its size, its shape, and roughly how it functions. Vision feels direct. Information seems complete. At cosmic distances, seeing is no longer direct, it is interpretive. The James Webb Space Telescope does not take pictures in the way our eyes do. It collects light at specific wavelengths and records how much arrives over time. From this, images are constructed, but those images are the final step of a long chain of processing. Before any galaxy is labelled ancient, its light is measured, sorted, and compared against physical models. This distinction matters because early galaxies are not identified by shape first. They're identified by colour, more precisely, by the absence of light at certain wavelengths and the presence of light at others. This pattern is called a spectral break, and it is one of the primary tools used to estimate redshift. Here is how the intuition breaks. We imagine that a galaxy's light is simply redshifted smoothly, like a rainbow sliding to the red. But the universe is not transparent at all wavelengths. Neutral hydrogen absorbs high-energy ultraviolet light. In the early universe, large amounts of neutral hydrogen existed between galaxies. As a result, light below a certain wavelength never reaches us. When Webb observes a galaxy that appears bright in infrared but disappears abruptly at shorter wavelengths, it is seeing the imprint of both cosmic expansion and cosmic absorption. The location of this cutoff tells us how much the light has been stretched, and therefore how old the galaxy likely is. This method is powerful, but it is not absolute. It produces candidates. Confirmation requires spectroscopy, where light is spread into its component wavelengths and specific features are measured directly. Spectroscopy is slower, more demanding, and harder to perform on faint objects, but it provides firmer ground. This is why early Webb announcements often used careful language: candidate, probable, consistent with high redshift. These words are not hedges, they are markers of where observation ends and inference begins. We pause again to restate what we now understand. At extreme distances, we do not identify galaxies by appearance alone. We identify them by how their light has been filtered by the universe. Seeing becomes pattern recognition guided by physics, not direct perception. Now we introduce another scale resolution. Webb has an extraordinarily large mirror, over 6 meters across. This allows it to collect faint light and resolve fine details, but even Webb cannot see individual stars in the earliest galaxies. What it sees is blended light from billions of stars compressed into a tiny patch of sky. To understand how small, imagine holding a grain of sand at arm's length. The area covered by that grain contains thousands of galaxies in deep field images. Each ancient galaxy Webb studies occupies a fraction of that grain. Within that fraction are structures spanning tens of thousands of light years. This scale mismatch is critical. We are inferring global properties from unresolved light, stellar mass, star formation rate, age distribution. These are not directly observed. They are inferred by fitting models of stellar populations to the observed spectra. These models are built from physics. We understand well how stars of different masses emit light, how they age, how dust absorbs and re-emits radiation. But applying them to the early universe introduces uncertainty. Early stars may have formed under different conditions. Dust properties may differ. The initial mass distribution of stars may not match what we see today. This is not a weakness. It is an explicit limitation. Astronomers do not claim certainty where it does not exist. Instead, they test ranges of models and report which are consistent with the data. When Webb uncovers a galaxy that appears surprisingly massive at high redshift, the immediate response is not to declare a crisis. It is to ask what assumptions went into that mass estimate. Could the stars be younger and brighter? Could dust be affecting the colours? Could active black holes contribute light? Each question is investigated systematically. Some candidates shrink in mass estimates. Others remain stubbornly large. Over time, a statistical picture emerges. This slow accumulation of evidence is invisible in headlines. One of the oldest galaxies ever seen sounds definitive. In practice, it is provisional, contextual, and continuously refined. Another intuition must now be replaced that galaxies have clear boundaries and identities. In the early universe, this is often not true. Many early galaxies are irregular, clumpy, and actively merging. What we label as a single galaxy may be several systems in the process of becoming one. This complicates interpretation further. A bright region may not represent a stable galaxy, but a transient burst of star formation triggered by interaction. Over time, these bursts fade or merge into larger structures. Webb's resolution helps reveal this complexity, but it cannot always disentangle it completely. Again, we are operating near limits. Let's anchor this with repetition. Early galaxies are faint, their light is stretched, their images are small, their properties are inferred, not directly measured. Each inference depends on models tested under extreme conditions. Uncertainty is not a flaw. It is a feature that tells us where the boundary lies. Now we address a subtle but important distinction: age of light versus age of stars. When we say a galaxy is one of the oldest ever seen, we are referring to the time when the light we observe was emitted. This does not necessarily mean all the stars in that galaxy formed at that moment. Some may be older, some younger. In practice, early galaxies often show intense star formation, meaning we are seeing them during a burst of activity. Their stellar populations may include stars formed tens of millions of years earlier. At cosmic dawn, tens of millions of years matter. This leads to a layered understanding of age. There is the age of the universe at emission. There is the age of the galaxy at emission. There is the age distribution of its stars. These are related but not identical. Headlines compress them into a single phrase. Science does not. We pause again. Our intuition now recognizes that oldest galaxy is shorthand. It means oldest light from a galaxy that we can currently detect and confirm. It does not mean the first galaxy. It does not mean the earlier structure. It marks the current observational edge. Another boundary appears here: selection effects. Webb sees what it is sensitive to. Bright. Star-forming galaxies are easier to detect than faint, quiescent ones. This biases the sample. The earliest galaxies we see may not be typical. They may be the most extreme. This does not invalidate the observations. It contextualizes them. As surveys expand and exposure times increase, fainter populations may emerge. Our picture will fill in gradually, not all at once. Now we return briefly to the human frame. We're used to photographs as records. At cosmic scales, images are not records of objects alone. They're records of interaction between object, space, time, and instrument. Webb's images are not deceptive, but they are incomplete by nature. Understanding this stabilizes us. We no longer demand certainty where physics does not allow it. We accept layered inference as the cost of reaching extreme distances. So when we hear that the James Webb Space Telescope has uncovered one of the oldest galaxies ever seen, we can hold the statement correctly. It means Webb has detected light whose spectral signature places it near the earliest era in which galaxies could exist. It means the object's properties challenge and refine our models, and it means that our understanding is provisional, grounded in observation, and open to revision as more data arrives. We end this stretch with a reinforced frame. Seeing at cosmic distances is an act of interpretation. Images are built from filtered light. Properties are inferred through models. Uncertainty is tracked, not hidden. And the phrase oldest galaxy marks a boundary we're approaching carefully, not a trophy we have claimed permanently. With interpretation now firmly in place, we encounter another intuition that must be dismantled, the idea that galaxies form slowly, quietly, and in isolation, following a calm, orderly sequence. This intuition comes from observing the universe as it is today. Modern galaxies appear stable. Star formation is measured. Mergers are rare on human timescales. Change feels gradual. The early universe did not behave this way. To understand why the James Webb Space Telescope is finding massive galaxies so early, we need to reconstruct the physical environment in which those galaxies formed. This requires shifting attention away from galaxies themselves and toward the medium that created them: gas, gravity, and dark matter. We start with density. The early universe was smaller than it is today. Not metaphorically smaller, but physically denser. The same amount of matter occupied a much smaller volume. This meant that gas clouds were closer together, interactions were more frequent, and gravitational collapse could proceed faster. Gravity operates on differences. Where matter is slightly denser, gravity pulls more strongly. In a dense environment, these differences amplify quickly. Regions that are just a little over dense attract gas from their surroundings. As gas falls in, it heats up, cools, and eventually collapses into stars. This process is not gentle. It is chaotic. Gas flows collide. Shock waves form. Radiation from newborn stars heats surrounding material. Some gas is blown away. Some continues to fall inward. Star formation happens in bursts, not in steady trickles. The James Webb Space Telescope is especially sensitive to these bursts. Young, massive stars emit intense ultraviolet light, which is then redshifted into the infrared. A galaxy undergoing rapid star formation will stand out strongly in Webb's observations, even if it is relatively small in total mass. This introduces another necessary correction. Early galaxies that appear bright and massive may not be mature in the way modern galaxies are. They may be experiencing brief, intense periods of growth. Our intuition wants to interpret brightness as maturity. At cosmic dawn, brightness often signals youth and violence. Now we introduce dark matter. It does not emit light. Webb cannot see it directly. And yet, dark matter plays a central role in early galaxy formation. It provides the gravitational scaffolding around which visible matter accumulates. In the early universe, dark matter began clumping even before normal matter could cool and collapse. These clumps, called halos, form the gravitational wells that trapped gas. The deeper the well, the more gas it could attract. The more gas, the more stars could form. This means that the earliest massive galaxies formed in the most massive dark matter halos. These halos were rare, but they existed. When Webb detects an unexpectedly massive galaxy at high redshift, one explanation is that it resides in one of these rare peaks. Again, this is not speculative. Simulations of cosmic structure formation predict a distribution of halo masses. Most halos are small, a few are very large. Early observations were biased toward average expectations. Webb's sensitivity allows us to detect the rare extremes. We pause and restate. The early universe was dense. Gravity acted quickly. Star formation was violent and bursty. Dark matter provided deep gravitational wells. Massive galaxies could form rapidly in rare environments. This combination erodes the intuition that early equals simple or small. Another intuition fails here, that feedback always slows growth. In modern galaxies, energy from stars and black holes can regulate star formation by heating or expelling gas. This feedback creates balance. In the early universe, feedback behaved differently. Gas was abundant, inflows were strong. Even if some gas was expelled, more could fall in. Feedback did not always shut down star formation. In some cases, it may have triggered further collapse by compressing surrounding gas. This means early galaxies could grow faster than their modern counterparts. They lived in a universe that actively fed them. The James Webb Space Telescope is not directly measuring these flows, but it sees their consequences: high star formation rates, compact structures, spectral signatures consistent with young, massive stars. All of these point toward rapid assembly. Now we introduce time again, but in a refined way. A few 100 million years in the early universe is not equivalent to a few 100 million years today. Conditions were different. Cooling times were shorter, densities were higher, interaction rates were faster. This is another place where human intuition misleads us. We instinctively map time intervals across eras as if the rules stay the same. In reality, the efficiency of processes depends on environment. The early universe was an efficient engine for building structure. We repeat this idea because it must settle. Early does not mean slow. Early does not mean empty. Early can mean fast, dense, and extreme. Now we confront a common misunderstanding. Some headlines suggest that early massive galaxies should not exist. This framing is misleading. What scientists actually mean is that earlier models underestimated how quickly galaxies could assemble under early conditions. Models are not laws. They are approximations constrained by data. When new data arrives, models adjust. The core physical principles remain intact. This distinction matters for cognitive stability. There is no collapse of understanding here. There is refinement. We also need to separate observation from interpretation once more. Webb observes light. From that light, astronomers infer star formation rates and masses. These inferences depend on assumptions about stellar populations. If early stars were systematically more massive than modern ones, they would emit more light per unit mass. This could make galaxies appear more massive than they are. This possibility is actively investigated. Spectroscopic measurements help constrain stellar properties. Over time, uncertainty narrows. Again, this is slow work. Webb does not deliver instant truth. It delivers pressure on existing frameworks. Now we step back and integrate. The James Webb Space Telescope is uncovering early galaxies that are bright, massive, and structured. This challenges simplistic expectations but aligns with a universe that was dense, dynamic, and efficient at forming stars. Dark matter halos provided scaffolding. Gas flows fed growth. Feedback operated differently. We pause and restate the stable understanding we have earned. The early universe was not a quiet beginning. It was an intense construction phase. Galaxies did not wait politely to form. They assembled rapidly wherever conditions allowed. This reframing dissolves the sense of paradox. Early massive galaxies are not anomalies demanding exotic physics. They are natural outcomes of known processes operating under extreme conditions. As we continue, the scale will shift again. We will move from how galaxies formed to how their light interacts with the evolving universe itself. But we do not announce that shift. It will occur because our current frame can no longer carry the load alone. For now, we end this stretch grounded. The James Webb Space Telescope is not revealing a universe that contradicts itself. It is revealing a universe that behaved exactly as gravity. Gas and expansion allow just faster, denser, and more extreme than human intuition expected. As our understanding of early galaxy formation stabilizes, a deeper assumption quietly collapses that galaxies shine into an already transparent universe. This assumption feels natural. We picture stars igniting, galaxies forming, and their light simply radiating outward into empty space. But for the earliest galaxies, the universe was not yet clear. It was partially opaque. Light did not travel freely everywhere. This changes everything about what it means to observe the first galaxies. After recombination, the universe became transparent enough for light to travel long distances, but that transparency was not permanent. As the universe expanded and cooled, neutral hydrogen filled intergalactic space. Neutral hydrogen is highly effective at absorbing ultraviolet light. For a long time, much of the universe was filled with this absorbing fog. This period is known as the Cosmic Dark Ages, followed by the epoch of Reionization. The Dark Ages were not dark because nothing existed, but because nothing luminous yet existed. The epoch of reionization marks the time when the first stars and galaxies began producing enough energetic radiation to ionize the surrounding hydrogen, stripping electrons from protons and making the universe transparent again. This process was gradual. It did not happen everywhere at once. It happened in patches. The James Webb Space Telescope is probing galaxies that existed during or near this transition. That means Webb is not just seeing galaxies. It is seeing them embedded in a changing medium that actively reshaped their light. Here intuition failed again. We tend to imagine transparency as binary. Either you can see or you cannot. In reality, transparency is partial, directional, and evolving. Early galaxies shone into regions of space that could absorb some wavelengths and transmit others. Their light carved out bubbles of ionized gas around them. These bubbles mattered. Within them, light could travel more freely. Outside them, it was suppressed. The size of these bubbles depended on how many stars a galaxy formed, how energetic they were, and how long they lived. When Webb detects a very distant galaxy, it is detecting light that successfully navigated this uneven landscape. That fact alone contains information. It suggests that the galaxy was luminous enough to ionize its surroundings, or that it sat near other galaxies contributing to a shared ionized region. We pause to restate. The early universe was not uniformly transparent. Light from early galaxies had to fight its way through neutral hydrogen. What we see is filtered not just by distance and expansion, but by the ionization state of the universe itself. This brings us to a crucial distinction. Webb is not directly observing reionization. It is observing galaxies during reionization, from their properties and distribution. We infer how reionization progressed. This inference requires care. If a galaxy appears faint in certain wavelengths, it may be due to absorption by neutral hydrogen, not intrinsic weakness. If it appears bright, it may reside in a locally ionized region. Interpretation depends on context. The cosmic microwave background provides independent constraints. It tells us when reionization was largely complete, based on how early photons scattered off free electrons. Combined with Webb's galaxy observations, a coherent picture begins to emerge. But coherence does not mean simplicity. Reionization likely unfolded over hundreds of millions of years. Some regions ionized early, others lagged. Small galaxies may have contributed significantly. Even if Webb cannot yet see them all, massive galaxies may have dominated locally. This layered process adds another axis of complexity. When we label a galaxy as one of the oldest ever seen, we are not only placing it early in time, we are placing it in a universe that was still becoming transparent. Another intuition dissolves here that observing earlier automatically means observing simpler. In fact, earlier observation often means more environmental interference. The signal is not cleaner, it is more distorted. Webb's infrared sensitivity helps because longer wavelengths are less affected by neutral hydrogen absorption. This is one reason Webb can see into the epoch of reionization, while earlier telescopes struggled. It is not just more powerful, it is tuned to the right regime. Now we need to address a subtle but important point. The galaxies Webb sees are not necessarily the ones that drove reionization. They are the ones that survived the observational filter. Many smaller, fainter galaxies may have existed in greater numbers, contributing collectively to reionization without being individually detectable. This selection effect matters. It means the earliest galaxies we study in detail may not be representative. They are the visible peaks, not the full landscape. Again, this is not a flaw, it is an acknowledged boundary. We pause and re-anchor. Early galaxies existed in a universe filled with neutral hydrogen. Their light was shaped by ionization bubbles. Webb sees those whose light escaped. Reionization was patchy, slow, and driven by many sources. Observation captures survivors, not the entire population. Now we shift slightly, because another intuition must be corrected. We often imagine reionization as something galaxies did to the universe, as if they were external agents changing a passive environment. In reality, galaxies and the intergalactic medium evolved together. Feedback flowed both ways. The state of the surrounding gas influenced how galaxies formed stars. Dense neutral regions could suppress star formation by limiting cooling. Ionized regions could allow gas to collapse more easily. This coupling means early galaxy growth cannot be separated cleanly from reionization. Webb's observations begin to touch this coupling. Variations in galaxy properties at similar redshifts may reflect environmental differences, not intrinsic ones. Two galaxies of similar mass may appear different because one sits in a more ionized region than the other. This complicates interpretation further, but it also enriches it. The early universe was not uniform, it was textured. At this point, we need to restate the cognitive frame. We're no longer just looking at galaxies as isolated objects. We are looking at galaxies as agents and products of a changing universe. Light is not merely delayed, it is filtered, absorbed, and selectively transmitted. This understanding prevents a common mistake over-interpreting absence. If Webb does not see a galaxy in a certain wavelength, it does not automatically mean the galaxy is not there. It may mean the universe between us and the galaxy is still opaque at that wavelength. This is why confirmation requires multiple lines of evidence. Imaging, spectroscopy, statistical samples, and theoretical modelling all contribute. Now we approach another boundary. As we push to higher redshifts, neutral hydrogen absorption becomes stronger. Eventually, even infrared light struggles. The observable universe closes in from both ends, technological limits from one side, physical opacity from the other. This boundary is calm. It is not a cliff. It is a gradual fade. So when the James Webb Space Telescope uncovers one of the oldest galaxies ever seen, it is doing so at a moment when the universe itself was transitioning from opaque to transparent. That galaxy's light carries not just its own history, but the history of that transition. We end this stretch grounded in clarity. The earliest galaxies did not shine into an empty, passive universe. They emerged within a fog of neutral hydrogen. Their light carved pathways through it. What Webb sees is shaped by expansion, gravity, star formation, and reionization acting together. Our intuition has now absorbed another replacement. Observation is not just about distance and time, it is about medium, and at cosmic dawn. The medium was still in the process of becoming clear. As the medium itself becomes part of the story, another intuition finally gives way, the idea that the universe we observe is a fair sample of what exists. At human scales, this assumption holds. When you look across a landscape, what you see is broadly representative of what is there. Hidden features exist, but they do not dominate your understanding. At cosmic dawn, this assumption fails completely. What the James Webb Space Telescope sees is not a neutral cross-section of the early universe. It is a highly filtered view shaped by physics, geometry, and chance. Some galaxies are visible not because they are typical, but because conditions briefly aligned to let their light escape, travel, and be detected. This is not a limitation of Webb alone. It is a property of observation at extreme scale. To understand this, we need to introduce probability, not as abstraction, but as physical reality. The early universe was uneven, density varied, ionization varied, star formation varied. Whether a galaxy becomes visible depends on where it formed, how fast it grew, how luminous it became, and what kind of intergalactic environment surrounded it. Two galaxies with similar intrinsic properties could have radically different observational fates. One might sit inside a large ionized bubble and be visible across vast distances. Another might be embedded in neutral hydrogen and remain hidden, even if it existed at the same time. This means visibility is not equivalent to existence. We pause here to restate carefully. When Webb detects one of the oldest galaxies ever seen, it is not telling us that such galaxies were common. It is telling us that such galaxies were possible, and that at least some of them were visible under the conditions that existed. This distinction matters because it reshapes how we interpret early discoveries. Early massive galaxies are not evidence that all early galaxies were massive. They are evidence that massive galaxies could form early and that some of them became observable. This brings us to the concept of cosmic variance. The universe is statistically uniform on very large scales, but on smaller scales, variation dominates. The early universe, in particular, was governed by local conditions. A small region could be unusually dense, unusually active, and unusually visible. Webb's deep fields sample tiny patches of sky. Each patch corresponds to a narrow pencil-like volume extending billions of light-years into the past. Within that volume, chance plays a role. One field might intersect a rare overdense region, another might not. This is why early results often show surprising objects. We're not yet averaging over large volumes. We're peering through keyholes. This is not a flaw in the data, it is a stage in exploration. Another intuition breaks here that seeing something early means it formed early relative to everything else. In reality, formation times overlap. Some galaxies may have begun forming stars earlier but remained faint. Others may have formed slightly later but grew explosively and became visible sooner. Time ordering becomes blurred. Visibility order is not formation order. This is difficult to internalize because human intuition wants a clean sequence. First galaxy A, then galaxy B, then galaxy C. The early universe does not present itself this way. It presents overlapping histories filtered by observation. We need to anchor this again with repetition. The earliest galaxies we see are not necessarily the earliest galaxies that existed. They are the earliest galaxies whose light survived the journey to us. Now we introduce another layer, gravitational lensing. Massive objects bend space-time. This bending can magnify light from distant galaxies behind them. Sometimes, a galaxy that would otherwise be too faint becomes visible because its light is stretched and focused by an intervening cluster. The James Webb Space Telescope frequently exploits this effect. It observes regions behind massive galaxy clusters specifically because they act as natural telescopes. The magnification can be dramatic. But lensing adds complexity. Magnification changes apparent brightness and shape. Distances must be corrected. Uncertainty increases. Still, without lensing, many early galaxies would remain invisible. This introduces another quiet intuition shift. The universe itself participates in observation. Space does not just stretch light, mass bends it. Visibility depends not only on what exists, but on how space-time is arranged along the line of sight. Again we pause. Observation at cosmic dawn is a collaboration between instrument, source, and universe. Webb is one component of a larger system. Now we return to statistics. As more observations accumulate, patterns begin to emerge. The number density of galaxies as a function of redshift, the distribution of brightness, the inferred growth rates. Individually surprising objects become data points in a population. This is where stability returns. Early discoveries feel disruptive because they are few. As samples grow, extremes become contextualized. Already, Webb data suggests that galaxy formation began earlier and proceeded faster than some earlier models predicted, but still within the bounds allowed by known physics. Adjustments are made, parameters shift, the framework holds. This process is quiet and methodical. It does not resemble revolution, it resembles calibration. Another intuition must now be dismantled that unknowns imply mystery. In this domain, unknowns are expected. They are mapped carefully. We know where uncertainty grows. We know why. We know what data would reduce it. For example, the contribution of faint small galaxies to reionization remains uncertain. Webb is beginning to probe this population, but completeness is limited. This is a known gap, not an enigma. Similarly, the initial mass function of the first stars is not directly observed. Models explore ranges. Constraints tighten gradually. These unknowns are not treated as invitations to speculation. They are treated as boundaries of current measurement. We pause again to restate the stable frame. What Webb sees is a biased, magnified, filtered sample of early galaxies. This sample is not misleading if interpreted correctly. It is powerful precisely because its biases are understood. Now we address another subtle intuition. We often imagine scientific discovery as revealing hidden truths that were always there, waiting, at cosmic dawn. Discovery is more like mapping fog. Features appear, fade, sharpen, and sometimes disappear as methods improve. Some early galaxy candidates may later be reclassified, their redshifts refined, their masses revised. This is not failure, it is convergence. The phrase "one of the oldest galaxies ever seen" is therefore provisional by design. It marks a moment along a moving frontier. This understanding prevents overreaction. It allows us to remain calm in the presence of revision. We now integrate everything so far. Early galaxy detection depends on formation physics, environmental transparency, cosmic expansion, gravitational lensing, and observational sensitivity. Each factor filters the population. What emerges is not the universe as it was in total, but the universe as it can be seen. This does not diminish the achievement, it defines it. We are approaching a point where adding more scale no longer clarifies intuition but overwhelms it. Before that happens, we stabilize once more. We now understand that early galaxies visible to Webb are rare, extreme, and informative. They are not representative, but they are real. They show what is possible under early universe conditions. This possibility space matters. It constrains models. It guides simulation. it shapes future observation. As we continue, attention will shift again, not outward, but inward toward what these early galaxies contain and what their light reveals about the ingredients of the universe itself. This shift is unavoidable, because distance alone can no longer carry the explanatory weight. We do not announce that shift, it emerges because the current frame has reached its limit. For now, we end grounded. The universe we observe at cosmic dawn is not the full universe. It is a filtered projection shaped by physics and chance. The James Webb Space Telescope reveals that projection with unprecedented clarity, and within it, the oldest galaxies we can see mark not the beginning of everything, but the beginning of what observation can currently reach. As visibility itself becomes conditional, our attention is forced inward, toward the light these early galaxies produce, and what that light tells us about their internal makeup. Another intuition dissolves here that a galaxy's light is a simple indicator of how many stars it contains. At human scales, brightness tracks quantity. More lights mean more sources. At cosmic dawn, brightness encodes something more complicated. Early galaxies shine differently. The light Webb detects from these ancient systems is dominated by young, massive stars. These stars are short-lived, extremely hot, and extraordinarily luminous. A single massive star can outshine thousands of stars like the Sun. In a galaxy undergoing a burst of star formation, these stars overwhelm the light from older, smaller ones. This means that luminosity is not a stable proxy for mass. A galaxy can appear very bright while containing relatively little total mass if it is caught during a brief, intense phase of star formation. Our intuition wants brightness to correlate with size. In the early universe, brightness often correlates with timing. We pause to restate. Early galaxies are not glowing steadily. They are flaring. This flaring matters because it shapes everything we infer. Stellar mass, star formation rate, and age are all derived from light. If that light is dominated by a particular stellar population, the inference must account for it. The James Webb Space Telescope allows us to do this more carefully than ever before. Its instruments can separate light into fine wavelength bands, revealing subtle features that indicate the presence of different types of stars. These features act like fingerprints. They do not tell us exactly what is there, but they constrain what could be there. For example, certain spectral slopes indicate very young stellar populations. Other features suggest the presence of heavier elements produced by previous generations of stars. The balance between these signals tells us how quickly a galaxy has been forming stars and for how long. Here, intuition failed again. We expect the earliest galaxies to be chemically pristine, composed almost entirely of hydrogen and helium. In reality, many early galaxies already show signs of enrichment. This means that stars formed, lived, and died even earlier, seeding their environment with heavier elements. This enrichment affects cooling. Gas with heavier elements cools more efficiently, enabling faster star formation. This creates another feedback loop. Once star formation begins, it accelerates its own continuation. The light Webb sees carries this history, not as a narrative, but as a statistical imprint across wavelengths. Now we introduce dust. Dust is made of heavier elements. It absorbs and scatters light. In modern galaxies, dust plays a major role in shaping observed spectra. In the early universe, dust is less abundant, but not absent. Even small amounts of dust can significantly alter observed colours, especially in galaxies dominated by young stars. Dust can make a galaxy appear redder, mimicking the effect of extreme redshift. Disentangling these effects requires careful modelling. This is another place where intuition struggles. We want a single explanation. In practice, multiple processes can produce similar observational signatures. Webb's advantage is not that it eliminates ambiguity, but that it reduces it by providing more data across more wavelengths. We pause again. Early galaxy light is shaped by stellar populations, chemical enrichment, and dust. Brightness reflects recent activity, not total history. Inference requires separating overlapping effects. Now we address another internal component: black holes. Supermassive black holes exist at the centres of many modern galaxies. Some appear very early in cosmic history. When actively accreting matter, they emit enormous amounts of energy, sometimes outshining their host galaxy. Webb is capable of detecting signatures consistent with active black holes in early galaxies. If present, these can contribute to brightness and alter spectral features. This complicates mass estimates further. Again, this is not surprising. It is expected. Early galaxies were sites of rapid growth, not just of stars, but of black holes as well. The presence of active black holes introduces additional feedback. Radiation and outflows can heat gas, suppressing or triggering star formation depending on circumstances. This interplay adds richness to early galaxy evolution. We repeat the stabilizing frame. The light from early galaxies is a composite signal. It blends stars of different ages, dust, gas, and possibly black hole activity. Webb's task is not to disentangle everything perfectly, but to constrain plausible combinations. Now we shift to scale again, but inward rather than outward. The regions emitting most of the light in early galaxies are compact. Star formation is concentrated. Surface brightness can be high, even if total size is modest. This compactness is another reason early galaxies can appear surprisingly prominent. Their light is not spread thinly across large disks. It is concentrated into small volumes. This matters for detection. A compact source stands out against background noise more readily than a diffuse one with the same total luminosity. This introduces another selection effect. Webb preferentially detects compact, intense star-forming regions. Again, this does not distort understanding if acknowledged, it refines it. We pause and re-anchor. Early galaxies are bright because they are young, compact, and actively forming stars. Their light is dominated by massive stars. Chemical enrichment and dust already play roles. Black holes may contribute. Brightness is a momentary condition. Now we confront another intuition that composition tells us origin directly. In reality, composition tells us process, not beginning. Heavy elements indicate that stars existed before, but not exactly when or where. The timing must be inferred statistically. This prevents a common misinterpretation. Seeing heavy elements in an early galaxy does not mean star formation began immediately after the Big Bang. It means it began early enough to produce enrichment before the observed light was emitted. The difference is subtle but important. We are now in a position to reinterpret earlier surprise. Early massive galaxies are not necessarily old in the sense of long-lived. They may be young systems experiencing rapid assembly and intense star formation shortly before we observe them. This reframing dissolves another false paradox. The universe is not producing mature galaxies instantly. It is producing rapidly evolving systems in an extreme environment. Now we integrate inward and outward frames. The environment sets the pace. Internal processes determine luminosity. Observation filters outcomes. The James Webb Space Telescope reveals this interplay through light that carries layered information. We pause again to stabilize. At this stage, our intuition about what a galaxy is has changed. It is no longer a static island of stars. It is a transient configuration of gas, stars, dust, and black holes, evolving rapidly under early universe conditions. This understanding will be essential as we approach limits again, because as we push further back, light becomes not just faint, but simpler, fewer elements, fewer generations, less internal complexity. The signals Webb sees will change character. We do not announce that transition. We simply note that the current frame-rich internal structure revealed by light will eventually thin out. For now, we end this stretch with clarity. The oldest galaxies Webb uncovers shine the way they do because of who they are at the moment we see them. Their light reflects intense, compact, rapidly evolving systems shaped by early universe conditions, interpreting that light requires abandoning simple links between brightness and size, age and maturity. Our intuition has adjusted again, and it is now ready for the next constraint, where even these internal clues begin to fade. As internal complexity begins to thin, we approach another boundary where intuition fails quietly rather than dramatically. We tend to assume that the farther back we look, the more clearly origins should reveal themselves. Earlier should mean purer, simpler, closer to the beginning, but at the edge of observation, the opposite happens. Signals do not become clearer, they become thinner. This thinning is not conceptual, it is physical. As we move toward higher redshift, galaxies become fewer, fainter, and less chemically enriched. The light Webb receives contains less information, not because the universe is hiding it, but because there is less structure available to imprint upon that light. Fewer generations of stars have lived and died, fewer heavy elements exist, fewer complex processes have had time to operate. This introduces a critical transition. Earlier, we relied on rich spectra to infer mass, age, and composition. Now, those spectra flatten, features weaken, distinctions blur. Here intuition breaks again. We expect fundamental truths to stand out more starkly at the beginning. In reality, early cosmic signals approach uniformity. Variation diminishes. This is not because the universe was simple in an absolute sense, but because differentiation was still underway. Gravity had not yet had time to sculpt extremes. Chemistry had not yet diversified. Feedback had not yet layered complexity upon itself. The James Webb Space Telescope is approaching this regime. Some of the oldest galaxy candidates show spectra that are sparse, dominated by broad trends rather than sharp features. This makes interpretation harder, not easier. We pause to restate. The oldest observable galaxies do not announce themselves with clarity. They whisper through minimal signals stretched to the edge of detectability. Now we introduce another distinction: detection versus characterization. Webb can detect galaxies deeper into the past than it can fully characterize them. Detection requires fewer photons. Characterization requires many. This difference matters. We may know that a galaxy exists at a given redshift without knowing its detailed properties. We may know its approximate age without knowing its mass precisely. This is not a failure. It is a hierarchy of knowledge. As we push toward the earliest galaxies, we accept that certainty decreases smoothly, not suddenly. Another intuition dissolves here: that scientific progress proceeds by filling in gaps. At this boundary, progress often proceeds by defining limits. Knowing what cannot yet be measured is itself an advance. For example, identifying the redshift beyond which galaxies become exceedingly rare constrains models of star formation. Measuring how galaxy brightness declines with redshift constrains how efficiently stars formed at early times. Even non-detections carry information. This requires a different cognitive posture. Absence is not emptiness, it is data. We pause again. Near the edge of observation, we learn as much from what is missing as from what is present. Now we confront an unavoidable physical limit: photon statistics. Light from the earliest galaxies arrives in extremely small numbers. A detection may be based on dozens of photons accumulated over many hours. Each photon carries energy, wavelength, and arrival time. Together, they form a fragile signal. At this level, randomness matters, noise matters, background subtraction matters. Confidence emerges statistically, not intuitively. This is far removed from everyday seeing. Human vision integrates billions of photons effortlessly. Webb operates in a regime where each photon is precious. This shifts the meaning of seeing. Seeing becomes probabilistic. A galaxy is not simply there or not there. It is present with a certain confidence level, based on how strongly its signal rises above noise. This probabilistic nature is carefully tracked. Astronomers report significance levels, They repeat observations. They cross-check instruments. Over time, confidence grows or diminishes. Again, this is calm work. It does not lend itself to dramatic framing. Now we return to composition one last time. As we move closer to the first galaxies, heavy elements become rarer. This changes star formation. Without metals, gas cools less efficiently. Stars that form tend to be more massive. These stars burn quickly and die violently. This suggests that the very first galaxies may have been dominated by massive stars unlike anything common today. Their light would be intense but brief, their chemical signatures sparse. Webb may be glimpsing the tail end of this regime, not the very first stars, but the first systems influenced by them. This brings us to a quiet but important boundary. There is a limit to what electromagnetic observation can tell us about the very beginning. Before stars, there is no starlight. Before recombination, there is no transparent universe. The James Webb Space Telescope is not designed to cross this boundary. No telescope observing light can. This is not a technological problem, it is a physical one. This understanding stabilizes expectations. Webb is not a time machine to the Big Bang. It is a bridge to the earliest luminous structures. We pause and re-anchor. The oldest galaxies Webb uncovers exist at a threshold where information content is minimal. Their light is faint, sparse, and stretched. Interpretation becomes statistical. Certainty becomes graded. Now we integrate everything inward. Early galaxies transition from rich, complex systems to simpler, more uniform ones as we push back in time. Observation becomes harder, inference becomes broader, models rely more heavily on constraints than details. This does not weaken understanding, or it refines it. At this boundary, questions change character. Instead of asking what is this galaxy like, we ask how many galaxies like this could exist. Instead of how massive is it, we ask what range of masses is consistent. These are not lesser questions, they are appropriate questions. We repeat this stabilizing idea. Near the beginning, science shifts from description to constraint, from narrative to boundary setting. Now we address a final intuition in this stretch that reaching limits should feel disappointing. In practice, reaching limits is clarifying. It tells us where to stop extrapolating. It prevents false certainty. When Webb identifies one of the oldest galaxies ever seen, it is not promising that the next one will be older. It is mapping the edge. This edge will move slowly as techniques improve, but it will never disappear. We are now close to the point where adding more scale outward no longer helps. The next shift must come from perspective, not distance. We do not announce that shift. It emerges because the current frame has reached its explanatory capacity. For now, we end grounded. The oldest galaxies Webb reveals are not richly detailed portraits. They are minimal signals at the threshold of observability. They teach us not by abundance of information, but by scarcity. And through that scarcity, they define the calm, physical limits of what light can carry to us from the earliest universe. As scarcity defines the edge, our intuition makes one last, stubborn attempt to reassert itself the belief that deeper observation should eventually answer everything, that with enough power, enough time, enough resolution, the universe will yield a complete account of its beginnings. At this scale, that belief fails quietly, not because of missing technology, but because of how information itself behaves. The limit we are approaching is not just observational, it is structural. The James Webb Space Telescope operates within a universe governed by causal horizons. There are regions whose light has not yet reached us and regions whose light never will. This is not speculation. It follows directly from expansion. As space expands, some regions recede faster than light can traverse the growing distance between us and them. Their signals are forever out of reach. This introduces a boundary that intuition resists. We are accustomed to thinking of space as something we could, in principle, cross given enough time. In an expanding universe, this is not true. Some distances are not just large, They're dynamically inaccessible. This matters for the oldest galaxies we can see. When Webb identifies one of the earliest observable systems, it is not identifying the earliest system that ever existed. It is identifying the earliest system whose light lies within our observable horizon. We pause to restate. The observable universe is not the entire universe. It is the portion from which light has had time to reach us since transparency began. This distinction is essential. Without it, oldest becomes misleading. With it, oldest observable becomes precise. Now we introduce another layer of subtlety. The horizon is not static. As time passes, light from more distant regions reaches us. The observable universe grows, but it grows asymmetrically. Early light arrives slowly. Late light arrives faster. This means that what is observable at one cosmic epoch differs from what is observable at another. The James Webb Space Telescope is operating at a specific moment in this unfolding visibility. Our intuition wants a fixed map. Reality offers a growing window. This window is shaped not only by expansion, but by the speed of light itself. Light sets a maximum rate at which information can propagate. No signal can outrun it. This is not a limitation of instruments. It is a rule of space-time. As we push observation toward the beginning, light has had less time to travel. Fewer regions fall within reach. The universe we can see contracts toward its earliest luminous sources. This contraction does not imply emptiness. It implies inaccessibility. We pause again. There may have been galaxies forming earlier than the ones Webb sees. There may have been many. Their light simply has not had time to reach us yet, or never will. Now we confront another intuition that must be released, that observation reveals a timeline. At these scales, observation reveals a slice, not a sequence. We are not watching galaxies appear in order. We are sampling what is visible along our past light cone. The past light cone is a geometric structure. It contains all events whose light is reaching us now. Events outside it are not observable now, regardless of their importance. This geometry reshapes how we interpret discovery. Webb is not scanning backward in time evenly. It is intersecting a curved surface of space-time where distance and time are inseparable. This is why two galaxies at similar redshift may differ dramatically in apparent age or structure. They occupy different regions of the light cone shaped by local conditions. We repeat this stabilizing frame. Observation at cosmic scales is not chronological exploration, it is geometric intersection. Now we introduce the concept of cosmic variance again, but refined. At the edge of the observable universe, variance is amplified. Small differences in location correspond to large differences in environment and history. Sampling remains sparse. This sparsity is not resolved by longer exposure alone. It requires surveying larger volumes. But surveying larger volumes at extreme redshift is time-consuming and difficult. Trade-offs are unavoidable. Webb balances depth and breadth carefully. Deep fields probe faint sources. Wide fields probe statistics. Neither alone is sufficient. This is another intuition shift. There is no single best way to look early. Every strategy sacrifices something. Now we address a misconception that often emerges here. When limits are discussed, they are sometimes framed as obstacles to be overcome. At this boundary, limits are not obstacles. They are defining features of the universe. The speed of light is not a challenge to ingenuity. It is a condition of reality. Expansion is not a complication to be corrected. It is how space behaves. Accepting this reframes discovery. The value of Webb's findings lies not in approaching omniscience, but in mapping what is accessible and why. We pause again. The oldest galaxies we can see are not the universe's first chapters. They are the earliest pages that survived the constraints of space-time and physics to reach us. Now we turn inward one final time, toward the role of models. At this boundary, models do more than interpret data. They connect the observable to the unobservable. Using known physics, simulations extend beyond the horizon. They estimate what kinds of galaxies could exist earlier, how many, and under what conditions. These simulations are constrained by what Webb sees. They are not free inventions. This is where inference becomes disciplined extrapolation. We do not guess wildly, we extend carefully. This relationship between observation and simulation is essential. Webb anchors the models contextualize Webb. Without models, early discoveries would float without grounding. Without observation, models would drift without constraint. We pause and restate. Understanding at cosmic dawn emerges from the tension between what can be seen and what must be inferred. Now we confront one final intuition in this stretch that not seeing something means it does not matter. In cosmology, unseen components often dominate. Dark matter shapes structure. Dark energy drives expansion. Early unseen galaxies may have driven reionization. Visibility is not a measure of importance. This is why the phrase "one of the oldest galaxies ever seen" must be interpreted narrowly. It refers to detection, not dominance. The earliest visible galaxies may not have been the most numerous or influential. Again, this is not disappointing, right? It is clarifying. As we near the limit, our questions refine. We ask not what is beyond, but what does what we see imply. We use constraints to bound possibilities. This is a stable cognitive posture. It resists speculation. It respects limits. We now integrate the frame fully. The James Webb Space Telescope operates within an observable universe bounded by light speed and expansion. It reveals the earliest galaxies whose photons lie within that boundary. Those galaxies define not the beginning of everything, but the beginning of visibility. This understanding dissolves the last false expectation. There is no final image waiting beyond the edge. There is only diminishing access. We do not dramatize this, we accept it. As we continue, the final shift will not add scale or complexity. It will return us gently to the present, carrying this expanded intuition with us. We will not introduce new mechanisms, we will stabilize what we have learned. For now, we end this stretch with calm clarity. The oldest galaxies Webb uncovers exist at the edge defined by space-time itself. They are not endpoints of knowledge, they are boundary markers, and by understanding why they are boundaries, we gain a more accurate, durable sense of the universe we inhabit. As boundaries become clear, one final intuition loosens its grip, the idea that understanding the early universe should feel unfamiliar, alien, or disconnected from everyday reality. After so much scale, so much distance, so many limits, it is tempting to think that what we have learned belongs only to abstraction. But at this stage, the direction quietly reverses. The universe we have reconstructed begins to feel consistent, not strange. The early universe does not require new rules. It requires the same rules applied without the cushioning of human scale. Everything we have followed so far, light travelling at a finite speed, gravity amplifying small differences, matter cooling and collapsing, radiation interacting with gas, are processes we already understand. What changes is not the physics, but the environment in which it operates. Density, temperature, and time compress behaviour into regimes we rarely encounter. This realization stabilizes intuition. The James Webb Space Telescope has not forced us to abandon known principles. It has forced us to use them without simplification. We pause to restate. The oldest galaxies Webb uncovers do not exist because the universe behaved differently. They exist because the universe behaved consistently under extreme conditions. Now we address a lingering misinterpretation. Early discoveries are sometimes framed as rewriting cosmic history. In practice, they are refining it. The broad outline remains intact: an expanding universe, early smoothness, growth of structure, formation of stars and galaxies, gradual chemical enrichment. What Webb has done is populate that outline with detail where none existed before. It has filled in early chapters with evidence rather than inference. This distinction matters because it affects how we integrate new information. We are not replacing one story with another. We are tightening the resolution of the same story. Another intuition dissolves here that complexity must accumulate linearly over time. In reality, complexity can surge early under the right conditions and then stabilize or even decline. The early universe experienced rapid structural differentiation because gradients were steep. Later, as expansion diluted matter, growth slowed. This explains why some early galaxies appear surprisingly advanced, while many later galaxies evolve more gradually. It is not a contradiction. It is a consequence of changing conditions. We pause again. Complexity is not monotonic. It is contextual. Now we turn to a final act of integration. Everything we have discussed, visibility, bias, formation, internal structure, limits, feeds into how we should now hear the phrase "one of the oldest galaxies ever seen." We no longer hear it as a headline. We hear it as a precise statement with boundaries. It means this is a galaxy whose light was emitted when the universe was very young, whose photons have survived expansion, absorption, and dilution, whose signal lies within our observable horizon, and whose properties can be constrained by current models. Nothing more, nothing less. This precision is not cold, it is calming, it prevents false expectation, it prevents overreach. Now we address one final intuition that often resurfaces at the end of long explanations, the desire for closure, a first galaxy, a final answer, a moment where uncertainty disappears. Cosmology does not offer this, not because it is incomplete, but because the universe is not obligated to present itself in discrete milestones. The beginning of galaxies was not a single event. It was a process distributed across space and time. Some regions formed stars earlier, others later. Some structures grew quickly, others lagged. There is no universal timestamp for first galaxy. Webb's discoveries reflect this. There is no sharp cutoff. There is a tapering, a thinning, a gradual disappearance of detectable structure. This is not unsatisfying once intuition adjusts. It is consistent. We pause to restate one last time. There is no singular oldest galaxy in the universe. There are only the oldest galaxies we can currently see. Now we turn gently toward the present. The James Webb Space Telescope continues to observe. Surveys expand. Spectra accumulate. Candidates are confirmed or revised. The frontier moves incrementally. What changes is not just knowledge, but expectation. We no longer expect surprises to overthrow understanding. We expect them to refine it. This is a mature scientific posture. It emerges only after limits are acknowledged. Another intuition dissolves quietly here that science advances by shock. At this scale, science advances by patience. Now we integrate the entire descent. We began with a familiar idea looking at a faint galaxy image. That idea has been reshaped step by step. Distance became time, light became history, space became active, visibility became conditional, observation became probabilistic, limits became structural. At no point did physics change, only intuition did. This is the core outcome, not information, but recalibration. We pause again, deliberately. What we now carry forward is a stable frame. The universe is vast, old, expanding, and structured by simple rules operating under extreme conditions. The James Webb Space Telescope extends our reach within those rules. It does not transcend them. This stability matters because it allows curiosity without distortion. We can ask new questions without expecting miracles or crises. Now we address one final internal boundary. There will always be earlier times we cannot see with light. There will always be structures below detection thresholds. This does not diminish what is known. It defines it. Accepting this removes tension. The universe does not owe us completeness. We are now prepared for the ending, not as a conclusion, but as a return. We will not add new concepts. We will not push further back. We will return to the opening idea with a rebuilt intuition. For now, we end this stretch with clarity and calm. The oldest galaxies revealed by the James Webb Space Telescope do not stand as anomalies or mysteries. They stand as confirmations that known physics, applied patiently, can carry us to the very edge of what is observable and leave us stable there, without confusion, without awe-seeking, and without the need for final answers. We return now to the image we began with a faint smudge of light, barely distinguishable from the darkness around it. After everything we have rebuilt, that image no longer feels simple, but it also no longer feels mysterious. It feels precise. At the beginning, it looked like just another distant galaxy. Now we understand what it actually represents. It is light that left its source when the universe was young, travelled through expanding space, survived absorption by neutral hydrogen, was stretched into the infrared, diluted by distance, filtered by probability, bent by gravity, and finally collected by a mirror orbiting far from Earth. What arrives is not the galaxy itself, but a carefully constrained trace of it. This reframing is the final adjustment of intuition. We no longer think of the James Webb Space Telescope as seeing farther in a simple sense. We understand that it is operating at the boundary where seeing means reconstructing. Every photon is late, every image is partial, every claim is conditional, and yet, within those conditions, understanding is solid. When we say that Webb has uncovered one of the oldest galaxies ever seen, we now hear the full meaning. It does not mean the first galaxy, it does not mean the earlier structure, it does not mean a final discovery. It means that this galaxy's light sits near the current edge of the observable universe, at a time when galaxies had only recently become possible to see at all. This edge is not arbitrary, it is set by physics. Light moves at a finite speed, space expands, matter interacts with radiation, the universe transitions from opaque to transparent. These facts alone define how far back observation can reach. Webb did not change those facts, it learned to work with them. We pause here to restate, calmly and clearly. The oldest galaxies we see are not special because they violate expectations. They are special because they satisfy constraints. They satisfy the constraint of forming early enough to exist. They satisfy the constraint of being luminous enough to emit detectable light. They satisfy the constraint of residing in regions where that light could escape. They satisfy the constraint of lying within our past light cone. They satisfy the constraint of being detectable by current instruments. Remove any one of these, and the galaxy disappears from view. This understanding stabilizes the entire narrative. There is no tension between theory and observation here. There is alignment under pressure. We also return to scale one last time, but without escalation. The distances are still vast. The times are still long, but they no longer overwhelm intuition, because they are no longer abstract. They are operational. Distance is how long light has travelled. Time is how far back we are allowed to see. Brightness is how much recent activity occurred. Absence is information about limits. These replacements are complete. Now we look again at the word old. In everyday language, old implies endurance, survival, longevity. In cosmology, old simply means early emission. The galaxy may have existed only briefly in the form we observe. It may have merged, transformed, or disappeared long ago. What persists is not the object, but the signal. This removes another quiet misconception. We are not cataloguing ancient relics. We are intercepting moments. Each image is a slice through a process, not a preserved artifact. This is why there is no sense of finality. There is no single oldest galaxy waiting to be crowned. There is only a moving observational boundary that advances as sensitivity improves and recedes where physics forbids access. The James Webb Space Telescope has moved that boundary forward, not dramatically, not infinitely, precisely. We now return fully to the present. Webb continues to operate. Data continues to accumulate. Some early candidates will be confirmed, others will be revised, the statistical picture will sharpen, models will be adjusted. None of this requires a change in worldview, it requires patience. This patience is the final cognitive state this documentary was building toward. We're no longer tempted to overinterpret a single image. We're no longer unsettled by uncertainty. We're no longer expecting a narrative climax. Instead, we understand how knowledge grows at extreme scale. It grows by constraint, it grows by exclusion, it grows by mapping limits. And within those limits, understanding is robust. We also recognize what Webb cannot do. It cannot see before stars. It cannot see before transparency. It cannot see beyond the horizon. These are not shortcomings. They are definitions. Accepting them keeps intuition aligned with reality. Now we return one last time to the opening idea, without resetting it. A faint smudge of light, at first glance, unremarkable. Now understood as one of the earliest visible markers of galaxy formation that the universe allows us to observe. Not the beginning of everything, not the answer to all questions, but a reliable anchor at the edge of what can be seen. This is enough. The universe does not reveal itself all at once. It reveals itself where conditions permit. The James Webb Space Telescope has extended those conditions further back than ever before, not by breaking rules, but by respecting them. And with that respect comes stability. We live in a universe that is vast, old, expanding, and governed by consistent laws. We understand those laws well enough to know where observation ends and inference begins. The oldest galaxies we can see mark that boundary with quiet precision. This is the reality we inhabit. We understand it better now, and the work continues.